For the remainder of these notes, we're going to look at a special type of power series that we've already mentioned before. They're the Taylor series and the Maclaurin series. Remember, they are a power series because they do have an A sub 0 and an A sub 1 and an A sub 2 and an A sub 3, etc., and an A sub n. These are just a whole bunch of coefficients that we have, but they don't form any old pattern we care about. They form a very particular pattern with the derivatives on the top and the factorials on the bottom. And once again, don't forget that if we center this at 0, then we call it a Maclaurin series instead of a Taylor series. All right, so one big thing we should notice here is we are not using an approximately equal sign. We're using a precisely equal to. This original function is exactly equal to this series, which is exactly equal to this infinite series right here. And I think we've already talked about why this is true, so if you were paying attention, you already know the answer. The answer is because, drum roll, because of the infinity right here, because of this plus dot dot dot, because our series is infinite. All right, so that doesn't mean that we're always going to have the exact same domain with our original function as we are with our Taylor series. Sometimes we'll only have a finite interval of convergence, and we can check using exactly the tools we just saw before, using the ratio test to determine that interval of convergence. But sometimes, as we saw with e to the x up at the top, one of the earlier examples, we will get an infinite interval of convergence, and that means that the Taylor series actually equals the actual function for all real numbers. Okay, so let's refresh our memory how we build one of these things. This one is an odd one because we're centering it at c equals 2. Ordinarily we wouldn't do this, but sometimes they force us to kind of make things a little bit harder on ourselves. So it says find the Taylor series. In other words, we're going on forever. But first find the first 4 non-zero terms, and then we can find the general term. So we'll start with f of x. You might know a shortcut for this, but the shortcuts might get a little confusing if we notice not only are we changing the x to a 5x, we're also changing the center from c equals 0 to c equals 2. So I'm just going to do this the long way. I will take the derivative, and we'll get e to the 5x, but we also have the chain rule telling us to put a 5 out front. And the second derivative, we'll get e to the 5x again, but we've got another 5 out front. So 5 times 5 is 25. And then the third derivative, we have 5 times 5 times 5, which is 125. And the fourth derivative, we're going to get 5 times 5 times 5 times 5, which is 625. So that's just repeated chain rule over and over and over again. And one thing you might want to do at this point, it's not required to do it right now, but if you can figure out the pattern, maybe we could find an expression for the nth derivative of the function. And you might notice that we're just multiplying by 5 over and over again. This is 5 to the first for the first derivative, 5 to the second for the second derivative, 5 to the third for the third derivative, 5 to the fourth for the fourth derivative. So we're going to have 5 to the nth for the nth derivative, and the e to the 5x doesn't change ever. Okay, now we're going to look at, again, that c equals 2. In other words, we're going to find f of c. Whoops, let's actually put 2 in there. F of 2, c equals 2. So f of 2 is going to be e to the 10. E to the 10. And f prime of 2 is going to be 5, e to the 10. And f double prime of 2 is going to be 25, e to the 10. And f triple prime of 2 is going to be 125, e to the 10. And f quadruple prime of 2 is going to be, don't crash on me here, 625, e to the 10. And the nth derivative of the function, evaluated at 2, is going to be, oh dear, is going to be 5 to the n times e to the 10. So when we build this Taylor polynomial, I'm sorry, we're actually building a Taylor series now, right? So we're going to say that e to the 5x is exactly equal to, not approximately equal to, we'll take the e to the 10 as our first term. We're going to take 5e to the 10 times x for our second term, but it's not just plain old x. People tend to forget this, but don't forget this center of 2. So every time we put an x, we want to put that x minus 2. And then we've got 25e to the 10, but now we're going to start having to put those factorials on the denominator. Again, you could put a 1 factorial here if you wanted to, and a 0 factorial here if you wanted to, and that would continue the pattern. I tend to leave those off just because it makes it a little messier to put them in there. And we've got x minus 2 now raised to the 2, and then we've got 125 e to the 10 over 3 factorial times x minus 2 raised to the 3, and we've got plus 625 over 4, e to the 10, over 4 factorial times x minus 2 raised to the 4th, and that continues on and on and on forever. And we actually found the nth term of this, so I'm just going to go ahead and write it in summation notation, starting with n equals 0, going to n equals infinity, going on forever. We're going to take our numerator is going to be 5 raised to the n times e to the 10. Our denominator is going to be n factorial, and we're going to multiply that by x minus 2 raised to the n. And that is the Taylor polynomial centered at c equals 2 for the function e to the 5x. One thing it doesn't ask us to do is to find the interval of convergence, but I suggest that you give that a try and verify that actually the interval of convergence is all real numbers, okay? Which is always going to happen with your e to the x functions. All right, so some formal manipulations of these special Maclaurin series that we've already seen before. Remember, we already saw that e to the x and sine of x and cosine of x all follow a very, very pleasing pattern that can be continued on forever. So if we look at example 4 here, it gives us a function, it gives us a power series, and it asks us to take its derivative. So let's give this a try. If we take the derivative of this function, the 1 goes away, the x becomes 1, the x squared over 2, well, the 2 comes out front and cancels out with the 2 on the bottom, and we get x. And then the x cubed, well, let's do this off to the side, x cubed over 3 factorial. If we take the derivative of this, then we get 3x squared on the top, and we've got 3 factorial on the bottom. Please don't do the quotient rule here. And the 3 cancels out with the 3, but we still have a 2 on the bottom, right? I'm going to go ahead and write it as 2 factorial. So we've got x squared over 2 factorial. And if we try this with the next term, again, quotient rule is ridiculous here because the denominator is a constant. So please don't use it. And you'll notice that the 4 on the top and the 4 on the bottom cancel out, but we still have a 3 times 2 times 1 on the bottom, so we've got 3 factorial on the bottom, and so on and so on. And in fact, if we take the derivative of that nth term, we're going to get x to the n minus 1 over n minus 1 factorial. And if we actually go ahead and take the derivative of the n plus first term, we're going to get x to the n over n factorial, and this sure does look like exactly the same series we started with. What function do we know that has this property where you take its derivative and you get the same thing back again? Well, it's also another function that has an x-intercept at 0. I'm sorry, it has an x-intercept at 1. I'm sorry, a y-intercept at 1. If we find f of 0, we know that this is 1 plus 0 plus 0 plus 0 plus 0 plus 0, which is 1. If we find f prime of 0, we also get the same thing because f prime is the same thing. This is a function that we know. We know that this is e to the x. Right? E to the x is a magical function that when you take its derivative, you get itself back again. And if we try that for this next one, let's see, this is the same function, but this time instead of differentiating it, we're going to integrate it. So this x is going to become, this 1 is going to become x. This x, well, we'll bump the exponent up by 1, and we'll divide by the new exponent, so we'll divide by 2. And then this next term, this x squared, we're going to have x cubed, and we're going to divide that by 3. But we already had a 2 factorial down there in the bottom. And then this next one, this x cubed, is going to turn into an x to the 4th. We'll put a 4 down here, but we already had a 3 factorial, so we'll keep that down there, etc. And then if we keep on going, if we try this with the x minus first term, then we'll add 1 to the exponent to get the n, and then we'll get n times n minus 1 factorial. And this is going to continue on forever, but we took the antiderivative, so we have this constant of integration here. So that's going to be capital F of x. And they actually gave us an initial value of f of 0 equals 1. So that's c plus 0 plus 0 plus 0 plus 0 plus 0 equals 1. That means that c equals 1. So that means that we have f of x, capital F of x, equals 1 plus x squared over 2. Well, I can write that as 2 factorial, because 2 is the same thing as 2 factorial. And x cubed over, let's see, 3 times 2 factorial is 3 times 2 times 1, or 3 factorial. X to the 4th over 4 times 3 factorial is 4 times 3 times 2 times 1. That's 4 factorial. And we actually have generated the exact same series once again. So, again, this is the same, because when you integrate e to the x, you get e to the x back again.